Okay, so last time I didn't check, and that's why I'm doing it now. Um, so this was Get Equipped for IITJ Advanced. Uh, Question number one is correct. And all this is correct. Just question number six. That's incorrect. So they are saying that uh, B is also correct. That is CH3CONH4 also acts as a buffer. I don't have calculations for this, but I think what they're saying makes a little bit of sense. Like uh, when you do the calculation for, that's the proper derivation for for weak acid, weak base salt, you will see that the degree of dissociation of both of the uh, acids and the salts, those are like very similar, and that is of course when the concentrations are the same, right? That's only when you will have a salt. So the degree of dissociations, they are very much similar and they are comparable to one basically, and that means like they're not very close to one, they're just comparable to one. That is like they are 1/3 or 2/3 or something like that. And so what that means is like if you put a lot of these acid and base, then what will happen is that the solution will basically act like two different buffer solutions, right? So yeah, and the concentration like of, I mean the degree of dissociation will be such that both the equilibrium can be sustained simultaneously, and that's why only at some certain pH values like this salt can kind of exist properly, right? So when you try to put more H plus into it, one of the two buffers that we have created by using this salt, those will just grab basically that H plus or OH minus, whatever that thing is. Actually both will grab in some certain ratio, but yeah, so that happens. So yes, it can act as a buffer. I didn't have any idea that it would, because it doesn't look like a buffer, right? It looks like there's a small quantity of salt in there, and then it's giving off a bit of pH and stuff. But no, if it was a large quantity, for example, then it would act as a buffer basically, right? Next, the next strong thing is question number 9. So I don't know, man. This doesn't make any sense. Like equilibrium constant of water, it doesn't make any sense, does it? Because you know that concentration of H2O, that we kind of don't consider because it's constant, right? The activity is constant. We don't consider that in our equilibrium constant. So yeah, what does this actually mean? K equilibrium constant of water. I have no idea. Right. And that is bigger than K. Ionic product of water aren't both the same thing. So then maybe A is wrong. Okay. But then they give B as a correct thing. So why would that be? I don't understand this. Okay. And yeah. And what next is wrong? It's question number 2. Ninth, I was not understanding what was the answer, and they gave C as the answer. So equilibrium constant for the reaction of BOH with HA at, so it's 10 power 9 for some reason. Like I don't know. I don't know why it's like that. Yeah, it just is. Probably it's just like BOH plus H plus that reaction. So you know, like BOH gives B plus plus O minus OH minus. For that, we figured out that the uh, KB value was 10 power negative 5. So when you have H, like BOH plus H plus gives B plus H2O, that's basically KW. No, not KW. It's going to be upon KW, right? So KB upon KW. And that's like 10 power negative 5 upon 10 power negative 14. That is 10 power 9. But then, like, Where's HA involved in it? It's just H plus. You should have said that it's H plus if you wanted it like that. I mean, okay, it makes sense when you're saying HA, it's just H plus. The A is not doing anything, it's just roaming around. And even if you consider it in the equation, like BA and B plus plus A minus, it's the same thing basically. So yeah, both have the same Gibbs free energy, almost same, that is, right? So strong electrolyte and stuff, it works out. But still, just say it's H plus. Come on, why HA? Whatever. So that was all that was wrong. And now we'll go to matrix match. Okay, so there we go. H3PO3, that's orthoboric acid. This is a Lewis acid and not a proton donor. So yeah, it's a reducing agent. I don't know. It's a monobasic acid. Yes, it gives BOH4 minus plus H plus. So yeah, it's a monobasic acid, right? It's a tribasic acid. No. So AP. Is it a reducing agent? I mean, like BH3 is, but BOH3, I don't think it's a reducing agent. So let's go for it first. Oh, okay, sorry. Now it should be correct. All right, so now it's correct. What are we doing? First, so A goes to oh, come on, seriously, man, this spoils all the fun. Yeah, it says it's connected, it's not. This is gonna take forever. Okay, so A goes to it's a monobasic acid, P. That's all we know about it. B goes to, so H3PO3, huh? So like PO H3PO3OOH. That's H3PO3, and that is, or you could also write it like this, POH, which I don't like to do because yeah, if you can form double bonds, why not? So H3PO3, it's like dibasic. It's not tribasic. It's not monobasic. It's dibasic. It's a reducing agent. I don't think so. Like, no. It okay. Actually, it can act as a reducing agent, but it's not used like that because you can get stronger reducing agents. But yes, so this pH bond, it has reducing character in it. So we can kind of use this as a reducing agent, right? This can be oxidized to POOH, OH, OH like that, and this is like pretty stable, H3PO4. So okay, PR maybe, I don't know. C, H3PO4. Well, that's definitely not a reducing agent. So it's a tribasic acid, yes. Then D, which is H2SO4. It is a good oxidizing agent, so it's not a reducing agent, and it's a dibasic acid once again. And what's it? It's a proton donor, yeah. So it's Q. That's all we can say about it. This is Q. Both B and C are proton donors, so both of them have Q, right? And A doesn't have Q, it just has P like that. Okay, question number 2. So what's this? Aqueous solution at 25 degrees Celsius. Fine. Equimolar CH3COH plus CH3CO minus, basically like that. Move that Ca2 plus on the side. So yeah, it's a buffer solution. And what is this? pH and POH. Hey, how am I supposed to know that? Come on. Okay, first of all, D goes to Q. We can surely say that. This thing is also buffer solution as given by the gods of the answers. Okay, whatever. There's an exaggeration. So A goes to B. It might also go to either of R and S. So this thing like equimolar, right? So there's more CH3CO minus. That means it's a basic buffer, or I no wait, why would be a basic buffer? Like CH3COOH, it's an acid, right? It has. Is this a basic buffer? Is this? I don't know. I just don't know. Like CH3CO minus. What's the backward reaction? What's the forward reaction? Ah, without data, how am I supposed to do any of this? I don't know. Okay, B. NH4Cl plus NH4OH. Well, that it's NH3 and NH4 plus basically. I think because it's equimolar, I think that it's acidic, right? Because yeah, like how much can NH3 survive with an H plus on it? I don't know. So it might be acidic. We have no idea, but it's also buffer solution. So B goes to P. CH3CO, it's also buffer solution. But D is not a buffer solution, right? They should have provided us with the Ka and Kb values, right? Okay, NaCl is pH equal to 7 for sure. And yeah, third, acidic solution. Huh? pKw equal to 13. Wait, what? pKw equal to 13, then pH would be 7.5. So what? That doesn't make sense. 7.5. 10 power negative 7.5. Oh, okay. So this quantity is definitely bigger than 10 power negative 7.5, right? And that means, yes, it's an acidic solution. So A goes to Q. 10 power negative 7 molar HCl at 25 degrees Celsius. Of course, it's an acidic solution, but it also goes to P. What else? Does it go to R? 10 power negative 7 at 35 degrees Celsius. What happened? Why did this? No, this didn't stop recording, did it? No. Okay. And A also goes to R, I think, because 10 power negative, no, 10 power negative Celsius, like base, is neutral, right? 35 degrees Celsius, then that's gonna be actually a little more than that, right? At 25 degrees Celsius, it's 10 power negative 14. At 35 degrees Celsius, it's gonna be more than that. We don't know how much more, but it is more than that. And what would it be? It would be like, I don't know. Whatever, at least more than that. So this quantity is less than what it should be, then that means OH minus is more than what it should be. Yeah. Right, so it's a basic solution. So B goes to R. And what about S? Pure water at 75 degrees Celsius. Well, it's also neutral, of course. So C goes to S, and D is H plus bigger than OH minus. That's acidic solutions. So it's like whatever A has, the same thing it will also have. Yeah. Next. Fourth, FeNO3 twice aqueous. It's only got Fe2 plus what, like only cationic hydrolysis. I mean, yeah, HNO3 is a strong acid. I think it's only cationic hydrolysis. Or maybe there's no hydrolysis. Does Fe hydrolyze by itself? It's a metal, right? And Fe2 plus. No, it does, in fact. Like, you form rust and stuff when you put iron stuff in water. So this might actually be hydrolyzing. So we'll say it's cationic hydrolysis. So A goes to P, and it also goes to anything else. Okay, all four are different. Fine. KClO4, ClO4. K plus is not changing much. ClO4, it's very oxidized. You need to get that reduced. So yeah, ClO4 minus. Yeah, it could change, and then we could have a, a bunch of oxygen leaving. Like no, it's just HL. Like it's just HClO4. That's what's gonna happen. Just wait a second. Sorry. Where were we? It's my fourth A. Right. So A goes to P. Only cationic. Sorry. A also goes to K goes to something else. D KClO4. I don't know. Both look like it looks like a good electrolyte. I mean, like HClO4. It's a strong acid, isn't it? Is it weak? No, it can't be. It's like so oxidized. It's got. I mean, the negative charge on ClO4. That will just be so stable. Like, how can it be a weak acid? Doesn't make sense. If it's gonna react anyway, it's gonna react in a way in which it will get reduced, and that's not acid base. So no hydrolysis, right? P goes to S. At least no practical hydrolysis. Like there's nothing happening practically. What does C go to? HCONA. Right, it's hydrolysis. It's anionic hydrolysis. So Q. D goes to NH4CN. So it's both cationic as well as anionic. Hey, that was easy. Shrink it down. Just wait a second. It will be over in a bit. Ah, come on. Okay. I'm just creating more space. Okay, let's go for the fifth one. pH of 0.1 molar HA, pK is 5 and 0.01 molar NaA. Huh. What about it? Like, oh, so these two mixed together or something, right? So in a solution which contains both of these, yeah, or like these individually. I think both of them at the same time, right? Then what? Like A minus upon HA, that quantity is just 10 power negative 1, right? So concentration of H plus, that will be 10 power negative 4. So pH will be 4. So A goes to B. Then what does B go to? pH of 0.1 molar BOH, pKb is 6, and 0.1 molar. Oh, cool. So BOH, B and B plus in the same quantity. So ignore that. And concentration of OH minus, that is 10 power negative 6. So POH is 6, pH is 40 minus 6, which is 8. So B goes to S. C. pH of 0.1 molar salt of weak acid and weak base. Right. So yeah, what was it? It was like pKa minus pKb upon 2 or something like that. No, I don't remember it. The main thing about the whole calculation was that um, it was the same degree of dissociation, right? Yes. So 0.1 molar weak acid, so 0.1 into alpha upon 0.1 into 1 minus alpha, yeah, times concentration of H plus. We don't know from what this is, right? I mean, okay, there's actually like, if this is the same degree of hydrolysis, then what will happen basically is that the H plus and OH minus created will be destroyed basically. So the H plus and OH minus concentrations are actually like very small in fact, right? Or either that they are just pre-existent, and because like maybe these concentrations are very big or something. Okay, and this thing is what was this, like Ka, and similarly 0.1 or whatever concentration there was in fact, and this will also be the same concentration, same degree of dissociation. Concentration of OH minus is Kb, and then if you divide this concentration of H plus upon concentration of OH minus, that will be Ka upon Kb. But then you know what this thing is, it's just Kw upon concentration of H plus. So this is like this guy squared, but Kw over here. So that means 2pH equal to, that was over there, Kw, okay, pKw plus pKa minus pKb. Cool, and that means pH is just half of pKw plus pK A minus pKb, I think, yeah. Cool. So what's it gonna be? pKw is just 14, so half of 14 plus, what is pKa? Which question was this? C, right? So Ka is, sorry, pKa is 5 and this thing is 7, and that's gonna be 12.26. so pH is 6, so R, pH of 500 liter of 0.2 molar HNO3, okay, and 500 liter of 0.2 molar BaOH2. So when you add them together, it just becomes 0.1 molar HNO3 and 0.1 molar BaOH2. And yeah, it's like a strong acid and stuff. This is also a strong base, I think, right? So it will take away one OH minus from this, and it will just be BaOH minus, and yeah, like 0.1 molar BaOH minus, and that's like a good base basically. Yeah, of course, that is, sorry, not minus, BaOH plus, right? And that's still a good base because it can only go forward, not backward. Or okay, if you gave us like the actual values, then that would make more sense, but you don't give that, so we'll just assume that okay, BaOH2 was very basic, and because like barium is, it's pretty low, right? It comes after calcium, I think, like, yeah, so it should be metallic, I think. If it's metallic, like very metallic, then it's gonna be very basic, right? BaOH, it's basic, and it's a very good base. So yeah, it's just 0.1 molar OH minus in the end in that case. So your POH is 1, your pH is 13, so Q. Then let's go to 6th. Why is this over here? Okay, let's go to 6th. Okay, CH3COH plus CH3CONA. This is 0.1 molar. And this is given. Okay, pK is given, and this is also 0.1 molar. Okay, that's nice. So yeah, pK is the pH. So pH is 4.74, which is definitely less than 7. Yeah. There we go. A goes to R, also to Q, and also to P, in fact. Wow. So what does B go to? CH3COH 0.1 molar plus HCl 0.1 molar. So it's just acidic, very acidic basically. Right, so it's just pH less than 7. It's not a buffer solution in any way. So P goes to R. C. CH3COH, pKa is given plus NH4OH. Fine, so it's NH3 basically. That's gonna be CH3CONH4. Yeah, and I like, okay, both of them 0.1 molar. Cool. Right, so pKa minus pKb, that thing. Oh wait, these are the same. Wow, that's very nice. And from the previous formula, right, it was independent of concentration and stuff. Yeah, and it was just Kw plus pKa minus pKb, I think, or it was the opposite. No, it must have been like, yeah, because no. If your pKa is very big, for example, then okay, in that case it will be more basic because it's gonna go back less. No, wait. No, if your pKa is very, it must be acidic, of course. It must be acidic. Yes. So then your pH must be half of like pKw minus Ka. Okay, it's getting complicated. Okay, come on. Concentration of H plus upon concentration of OH minus, that guy is just Ka upon Kb, right? And that's how it is basically. Or is it? Yeah, it is in fact. Right. Yeah. That makes sense. Okay. Then that just means it's like this is Kw upon concentration of H plus this squared. Then yeah, it's just pKw plus pKa. Oh yeah, if your Ka is big, your pKa is smaller. And that means it will work like that. Yes, it's correct. So yeah, pKa minus pKb is 0 anyway, so we don't have to care about it actually. So it's just like 7. It's pH equal to 7. C is S. Right, CH3CONA plus HCl. Okay, 300 milliliter of 0.1. Okay, this is, so it's a buffer, right? And now that you have given us the value, like pKa is this guy, we can deal with it. Right, so what's it? Plus HCl, how much? This much. 0.1 molar. Okay, cool. So now it's 400 molar, right? Oh, this changed by 3/4. Ooh, that is not nice. So initially it's like you had 30 millimole of CH3CONA, which is the same, it's A minus, and then plus 10 millimole of H plus. Well, that converted it to 10 millimole HA and 20 millimole of A minus. Yeah, and it's about 400 milliliter of volume. Right, so this is going to be 1/4 molar HA and 3/4 molar A minus. There we go. But the basic thing is just that A minus upon HA, that thing is just 3. Okay, so 3 times concentration of H plus, that is your Ka. So your pH is now pKa plus log base 10 of 3. Yeah, so it's going to be going over there 1 upon 3 and then it's 3 upon negative 1. That's why it's plus, not minus, right? And pKa is, well, you already gave us, it's just 4.74 plus, so log base 10 of 3, it is approximately 0.478 maybe. I'm gonna say 0.48 and not 0.477 something in the front, which I don't remember. Yeah, and this is gonna be zero, like what? 5 points. It's gonna be 2, 1 carried on, 5, so 2 over there. Yes, so 5.22, that is your pH for this. So D goes to R, right? C goes to S, D goes to R. So hey, it's a buffer and it's also like acidic, so it should also go to Q in fact. So yeah, and anything else? Oh, C also goes to Q in that case because this can also act as a buffer solution, right? Yes, that's how it is. Anything else? More of these? No. So just check it. And yeah, wow, that's a lot of questions. Matrix match. So A goes to P, then Q and R, yes, then Q and S, yes, yes. P and R, okay. P and S, okay. P and Q, okay. You didn't give any data on that question. How am I supposed to know anything about it? Okay, third. A goes to P, Q, X goes to R. Then C, where is it? C goes to S. Then EQ. PSQR. Then wait, PSQR once again. Huh, that's nice. No, PSRQ. Is it PSRQ? Shift 5. Yeah, it is. 6. PQR. Yeah. Then just R, then QS, and then hey, that is nice. I did almost everything correctly except like I didn't guess these 3. So maybe I need to actually memorize some pH values. Whatever. Or I could have just copied it from some other question. But then that's kind of cheating, isn't it? And also not reliable because who knows, maybe their values are not correct. They just it's hypothetical values. Whatever. So that's it. I'll see you guys in the next video.